started. We're now in session 2. We had a big group also before lunch where we went through basically bottom pressures in the software. The idea behind this kind of yearly course series is just to do a deep dive on specific functionality in Whitson Plus. So not like a full work or anything, but primarily in this course we'll focus on BHP. Last in February we had a similar course on PVT properties. There'll be one on RTA, one on flow material balance, and also later than that will be one on nodal. The way we're going to do the course right now is that Stian is going to go through the theory part. That's going to take a little bit more than an hour. And then after that, we're going to take a little break, and then we're going to have an exercise part where we're basically going to put a lot of the things that Stian goes through in practice. And I'll go through that, or try my best at least to go through that exercise with you all. And then, of course, questions and whatnot can be asked whenever. So with that, Stian, I'll leave the floor up to you. And if there's any questions, just feel free to use the chat box to the right.
Yeah, thanks. Welcome, everyone. Good afternoon, I guess, for most of you now. I'm going to start this session, or first I'm going to introduce myself. I'm Stian Midland. I work out of the Stavanger office in Whitson. I'm one of the senior software engineers and the main caretaker for the BHP engine and calculations for done by the BHP engine. As Matthias said, we're going to start with the theory part. Full disclaimer, there may be a couple of equations, but don't be afraid. I'm going to discuss the heaviest parts in great detail. And like Matthias said, if you have any questions, just either shout out. Just make sure to stay muted when you're not talking so we don't have a lot of background noise during the lecture, and or use the chat. I'll try to keep my eye on chat while I'm talking, and Matthias is also there to answer any questions. Okay, so first, a little bit of general information. Some of this is already said, so I'll just skip through it fairly quick. It's a half-day course, 4 hours tentatively. We're probably going to use a little bit less, 3.5 or so. It's supposed to be an interactive class, so this first hour, maybe a little bit more, hour 10 minutes, will be more of a lecture kind, but we encourage you to ask questions and be active there also. And then the exercise part is more for you to try out the different feature and just get sort of the suite of the BHP calculations in Whitson Plus. Again, this we've said. The session is now being recorded. The recording will be made available to you all after we're done. The material or the presentation has already been sent out, and there's a couple of revisions, last-minute revisions there, so we'll send out the final version when the course is finished. And like I said, there are some equations in this slide deck. Not everything will be discussed in great detail. Some are just more for reference or just to have seen it. And that's about it. Regarding the exercises afterwards, we'll repeat this later today. I'm just going to mention it briefly now. So when we do the exercises, please use courses.whitson.com. Don't use your domain like you normally do. We've set up a set of wells for you readily on courses.whitson.com. There you log on with the email that you are attending this course with. And the password is Whitson BHP 2023. Again, we'll repeat this when we get to the exercises, but if you want to go in ahead before, you're welcome to do so. And if anything doesn't work, if you're blocked or something doesn't work, just send an email either directly to Matthias or to support@whitson.com, and we'll help you as fast as we can. So the agenda, like we've said now, 2 parts. First, some BHP calculation fundamentals. Sort of the headlines are given here in the bullet points, and then exercises. Okay, so BHP. First, we have to just set the stage and make clear what do we mean by BHP, or bottom hole pressure, flowing bottom hole pressure. And in Whitson Plus, that's defined as the well pressure at the top perforation depth, or the depth at the top of the perforated interval. There's two reasons for that. One is sort of a theoretical reason for it, and that's in the well, from the wellhead and down to the perforated interval. The top there is as far is as deep you can go without the mass flow sort of changing in the well. The rates you're recording at surface, or the rates you've provided to compute this bottom pressure, will be that mass flow will be the same all the way down. But from this point and to the heel of the well, the rate will change with each and every perforation. There will be some rate incoming that adds to the total mass flow. So that's the theoretical reason why we computed at that point. If you want to go deeper, sort of strictly correctly, then you would have to account for that inflow by using some sort of IPR or something like that. Then there's the practical reason for it, and that's just mostly because our wells, taught unconventional wells, they are essentially all horizontal in the perforated interval. And like we'll see, the majority of the pressure drop in that region is just, or the majority of pressure drop for any of these wells really is mostly due to gravity. And when you have a horizontal pipe, gravity doesn't contribute to any loss in pressure. So the pressure difference between heel and toe will be quite small compared to the pressure drop from the top perforation to the wellhead. That's really where the pressure drop occurs. But if you want to compute it at a different depth than the top perforation, you can always move that point by just specifying the top perforation in the wildcard. Or we'll get back to all of this, but I'm just noting it out there now that this number here, the top perforation MD, that's really where the BHP is being reported in measured depth, but you can move that point to anywhere along the well as long as you stay shallower than the end, or sort of the toe of the well. And that will show you the effect of like moving the reference point back and forth. Just note that they're not then accounting for the inflow of the well. You're then moving the whole mass flow just deeper into the well. Okay, so with that sort of said, we can ask the question, why do we calculate BHP? It's sort of obvious because we don't have them readily available. We seldomly measure them in taught unconventionals, and but we need them in many cases. Indirectly in DCA should be constant. Flowing material balance relies on it. RTA, both analytical and numerical, rely on it, and and numerical model rely on, and also nodal analysis, not on the list here, but that too relies on bottom pressures. So what are the inputs to a BHP calculation? If we can't measure it, we have to estimate it. And the input to estimate the pressure at the bottom of the well is sort of two parts. There's the production data and there's the well data. For the production data, the minimum we need to know is the rates of all three phases, gas, oil, and water, at standard conditions. 14.7 psi, 60 Fahrenheit typically. Then we also need to know the pressure and temperature at the wellhead. And there's typically two pressures at the wellhead. There's one called casing or casing head pressure, referring to the pressure measured in the annular space around the tubing, if there's a tubing. If there's not a tubing, it's just a wellhead pressure. And there's the tubing head pressure, which reflects sort of the pressure measured in the tubing at the wellhead. Those are the production data, the bare minimum. You can also have other things like lift gas rate, liquid levels, and these things for artificial lift methods. But at a bare minimum, to do a BHP calculation, we need those production data. Then we need to know something about the well. First, we need to know how the well looks. So, and that's described by a well deviation survey. Essentially 2 columns, measured depth versus a true vertical depth. And that tells us how much of a vertical change there is in the well, which is important for the gravity, and also the curvature of the well, or the inclination of the well. We also need to know how the well is completed. Diameters particularly matters in pipe flow calculations. So we need to know the inner diameter of the tubing, if there's a tubing there, and the innermost casing, the production casing. And if we're planning to flow in the annular space, we also need to know the outer diameter of the tubing to compute the diameter of the surface area of the annular flow space. Pipe roughness, more of a second order effect, but still required, reflects sort of the ruggedness, if you will, or the impurities in the pipe wall that amounts or has an effect on the friction loss. And we also need to know particularly where the tubing ends. That's often it's an important number in many cases in BHP. We'll get back to why. Okay, so BHP calculations. The inputs we've now gone through. So what are the BHP calculations? So in a nutshell, BHP calculations, we're trying to use single phase flow equations for pipe. Those are fairly simple and well defined, and apply those to a multi-phase flow problem. But to do that, we need to add together the three phases that we have into one sort of, call it a pseudo phase or some sort of pseudo mixture that we can apply to the single phase pipe flow equation. And the way that's typically done, or the way it is done, is the oil and water are assumed to flow with approximately the same velocity. Density differences between oil and water are not that big compared to the gas phase, so we typically lump those together into a liquid phase and then we use the correlations to lump the gas and liquid phases that are most often flowing with very different velocities in the pipe into a, call it a mixture velocity or sorry, a mixture, this one phase mixture that we apply to the correlation, to the pressure equation. And that averaging, last averaging from a gas liquid system into a mixture of all three phases, that's correlation dependent. So the pressure gradient, here's the first equation we'll see. It consists of three terms, not necessarily need to know exactly what all these symbols mean, but the point is just simply that there are three sources of pressure or three sources that adds or subtracts pressure depending if you go up or down. It's the gravity, it's just caused by the mere weight of the fluids. It acts in the direction of gravity, so in the horizontal section, this term goes to zero. There's friction, which is caused just by the pipe wall itself. And then it's the acceleration, which is seldomly a very relevant mechanism, but for gas-rich wells at low pressures near the wellhead, the gas may expand very rapidly, and you can get these acceleration effects that create some loss of pressure when you go up the well. But primarily, it's gravity and friction that amounts or amounts to the pressure loss in the pipe. The temperature, we also have a temperature change in the well. Going from the reservoir temperature to the surface, we assume that there is just a straight line linear relationship of how the temperature changes in the rock itself. So we provide some estimate of the rock temperature at surface, say in this case 60 degrees Fahrenheit. And at the reservoir, it's the same as the fluid. They're both at, in this case, 200 degrees Fahrenheit. This differential equation here, what it essentially does is that it is a simple approximation of how heat leaks off from the fluid that's flowing into the surroundings. That's what this means. That's what this T minus T rock represents, essentially. And you get this kind of curved shape. And we have to provide, so the reservoir temperature we know from the fluid definition, and the wellhead temperature we have to provide, in this case 100 degrees Fahrenheit. And then you can fit this equation to go through those 2 points. Okay, so that's sort of the single phase part of it. Now, how do we apply that to the multi-phase flow? Talked a little bit about it already, but now I'm going to go more into the details of the multi-phase flow itself. So multi-phase flow for BHP calculations is essentially a question of whether we account for what is called slip, or whether or not we account for that. And slip refers to the fact that gas or liquid can flow with different velocities. If we assume that there is no slip, that translates into saying that, well, both the gas and the liquid are flowing with the same velocity. There's no velocity difference between. There's the difference between gas and liquid velocity, Vg minus VL, that's the so-called slip velocity. But if there's no slip, then we assume that they're equal, and we can define sort of the fraction of liquid by just dividing the liquid rate to the sum of rates at any point in the well. Then we get this CL, the liquid flux fraction. And we can average the liquid and gas properties into one mixture using CL by just linearly weighing the liquid density and the gas density into a mixture density. And the same thing for viscosity, which also matters, especially for the friction. Now, if we account for slip, meaning that the gas flows faster than the liquid up the well, then we can't use the rates anymore to explain or to compute the amount of liquid at any point in the well in the cross-sectional area. Then we actually have to look at the definition of what that would be, dividing the liquid, the amount of in the total pipe cross-section area, how much of that area is occupied by the liquid phase and how much of it is occupied by the gas phase. And the liquid holdup is just the liquid area divided by the total area, the pipe area. And that's all. Liquid holdup is often in some other, not in petroleum engineering, it's most often called liquid holdup. In other industries, it's sometimes referred to as a void fraction, which is just 1 minus liquid holdup. And what you can see, if you flip these equations around a little bit, you can show that as long as Vg is greater than or equal to VL, then the liquid holdup is always greater than or equal to the liquid flux fraction, or the no slip holdup, if you will. So that's the limit. And what that means is that the liquid holdup will always be between 1 and the liquid flux fraction. It can't go below that. That would mean that the liquid flows faster than the gas, which physically makes little sense. And the liquid holdup, that number, that ratio there, is what we use to average the liquid and gas phases together into this, in this case denoted S for slip, but it's this same kind of single phase mixture. But in this case, it's computed differently as respect to this one, where rho m just stands for mixture, or sometimes denoted NS for no slip. There are different notations out there. So what is this liquid holdup? Well, what you can see from the equations is that CL, this is just a different way of writing what we just saw, but the point is simply that the consequence of using the liquid flux fraction versus using the liquid holdup is that if we use the CL, we're accounting for too much gas in the cross-sectional area. If the liquid and gas flows with different velocities, then using CL will account for too much gas, and will make our fluid will weigh the gas properties too much when we're computing the pressure profile of the pressure gradient in the well. And what we'll see in a couple of slides ahead is that that has an impact, in the sense that we will always predict a lower bottom hole pressure if we don't account for slip. That means using this number here instead of using the liquid holdup, which tries to account more correctly for what truly, if we were able to freeze time and make a cross section somewhere in the pipe, what would we see? That's what this number tries to estimate. And the correlations, the main objective of all the pipe flow correlations is to predict this number, the liquid holdup. Just nice to know, in multi-phase flow, there's very often talk about flow regimes, which can be sometimes in Beggs and Brill, they're used quantitatively to define how to compute the liquid holdup. They are more qualitative maybe than quantitative, in the sense that they only sort of give you a picture of what may be going on. But if you like this one here by Gould et al., you can plot a sort of a gas velocity, a dimensionless gas velocity and a dimensionless liquid velocity. And you can see that for low gas velocities and high liquid velocities, then the liquid phase is assumed to be the continuous phase in the well, and the gas sort of exists as bubbles percolating through the liquid. In the middle here, we have more of an alternating continuous phase. So there are sort of slugs of liquid and gas going up the well. And as we approach more low liquid rates, low liquid velocities, high gas velocities, we're more into where the gas phase is continuous and the liquid is sort of lifted out of the well as droplets and to some extent also just adhering to the pipe wall. So the pressure gradient, again, we're going to simplify it a little bit from the previous equation you saw. We're going to assume that this acceleration term can be approximated because it seldomly has a very big impact. And by that, we can solve for the dPds, the pressure gradient, explicitly as a function of the gravity term, the friction term, and this acceleration correction in the denominator. And the correlations, they provide ways of computing some of these properties. We'll get back to which one those is a couple of slides down. So just to show a little bit how this looks along the well, I'm going to look at show you three different kinds of fluid systems. A black oil, which is going to be kind of sort of very liquid-like with only sort of gas existing as bubbles, essentially. Volatile oil, more in the sort of the alternating phase, where there's going to be a lot of gas, at least as you approach the wellhead and the pressure reduces, a lot of gas is going to come out of solution and exist as free gas and expand very rapidly. And then a gas condensate where the well is essentially filled with gas, and the liquid is just moved up the well as droplets with that gas. The fluid systems, the three different, they're modeled with the same well, so the same well deviation survey and the same completion. There's no artificial lift here, just to keep it simple. And the first thing we can look at is the pressure profile. And here is what I mentioned a couple of slides back, was that when we use this CL, this liquid flux fraction, and we're essentially not accounting for slip, then we get the red line. And if we do account for slip, then we get the blue line. And you can see that the difference can be quite substantial in the predicted bottom hole pressure. The end of the curve here would be the number that you get when you're computing bottom hole pressures over time. This is the pressure at the wellhead. It's 200 psi in this case. And then we predict the profile down the well to the 7,000 feet, where there's a change in diameter, where the tubing, the end of the tubing is there, and then the remainder is a 5.5-inch production casing. And like in this case, you can see there's quite a bit of difference between the BHP when we're not accounting for slip and when we're accounting for slip. And the way you can think of it is that if there were no gas at all, these two lines would be on top of each other. So a single phase liquid would have a blue and red line on top of each other. Then as we increase the gas amount or make the system more multi-phase, the difference would become more and more substantial until the gas amount is so high that we're starting to approach a single phase gas system, and these two lines will come on top of each other again. So that means that there is some GUR here, or some GLR, maybe gas liquid ratio, that sort of maximizes the difference between these two. And that's where it's actually the most important to account for slip. Looking at the liquid fractions, the flux fraction and the liquid holdup, here you can see also there's quite a difference. One thing that's a little bit interesting with the black oil here, so they're computed with Hagedorn and Brown, the two, call it oil ones, and then the gas is computed with gray. You can see that in this case, the Hagedorn and Brown correlation is actually predicting a liquid holdup less than a liquid flux fraction, which I said we cannot have. It's always bounded by that. So in this case, where the lines are on top of each other until here the correlation predicts a liquid holdup greater than the liquid flux fraction, and they diverge again. For the volatile oil, you can see the liquid holdup is quite large in the casing part, but once you enter the tubing, the liquid holdup reduces, and that reflects the fact that in a smaller sized pipe, the velocities are higher. The gas that's there is going to flow faster in a narrower pipe, and it's going to lift more liquid with it. It has more kinetic energy per se to lift this out, and it reduces the liquid holdup. That's what this essentially reflects. And in the gray correlation, even more so, you see the same kind of thing. There's much more liquid left behind relative to the flowing gas in the production casing than in the tubing. If we look at the pressure gradient and which mechanism accounts for most of the pressure gradients, what I'm plotting here is each of the three. So gravity is the blue one, friction is the red one, and the green one is acceleration. And I'm plotting them as a percentage of the total loss or the total pressure gradient at any depth in the well. That's what we're looking at here. And what you can see is that gravity in the black hole case, when it's mostly liquid in the well, you can see gravity makes up for more than 80% of the drop or pressure drop along the well, and it's increasing towards maybe 90. And as we go into the casing, it essentially amounts to all of it, except here it starts to curve out again, and that's because the well is flattening out. We're entering the horizontal section where the gravity loses its effect. For the volatile oil, you can see at the wellhead, the friction, there's so much gas, free gas at the top of the well, that friction amounts to quite a bit of it. But as we go deeper, that more of that gas is sort of in solution in the liquid, and gravity makes up for more of the pressure loss. And in the production casing, there's a wider tubing, or the wider diameter, sorry. And in that case, the velocity of gas makes up for even less friction, and gravity dominates even more. And for a gas, you can see, at least for this well configuration, which is a quite typical one, 2 7/8-inch tubing down to some depth, and then 5.5-inch production casing the rest of the way. You can see that friction makes up most of the pressure drop in the tubing part, and then they have friction and gravity are swapping when you go into production casing. Again, for the same reason that the gas flow with much less velocity here, and the small amount of liquids that are in the well here will make up for more of the drop, or the pressure drop in that case. So the correlations, what do they do? How do we use the correlations? I'm not going to go into sort of detail of every correlation, the four that we have in Whitson Plus, but I'm going to say just what the common equation is and sort of the gist of how each of the correlations work. So again, coming back to this pressure gradient equation, this equation is common to all the correlations. What differs is how some of these properties are calculated with the correlations. So the gravity density, or the density in the gravity term, the multiphase friction factor, the density in the friction term, and the density in the acceleration term are the properties that are depending on the correlation. And the correlations have different ways of assigning these values when you compute the pressure gradient in the well. So the first one out is Hagedorn and Brown. I think that's the oldest one of the correlations we have. It's from 1965. And the way it works is essentially you compute 4 dimensionless numbers, and you go through 3 different plots where you have to read off graphically corresponding values, and you ultimately end up with a liquid holdup. That's one of the properties, and that liquid holdup is used to calculate a slip density, like we saw on a couple of slides back, which is assigned to the acceleration density and the gravity density. The friction density is this no-slip density squared divided by the slip density. And the friction factor is computed with a Moody diagram, or an equational equivalent of the Moody diagram, with a Reynolds number defined like this, sort of a geometrical averaging of with the liquid holdup of the viscosities. It's Hagedorn and Brown, the original equation, it was found out later that on the onset of gas coming out of solution, going from a single phase liquid to very early on having small amounts of gas in the well stream, the Hagedorn and Brown correlation could be a bit inaccurate. So it's very common to apply modifications suggested by Griffith, where you define a limit to where you have so-called bubble flow. And that limit, that flow regime, essentially, the boundary is when this 1 minus this liquid flux fraction is less than a maximum of that equation, or 0.13. If this is true, then we have bubble flow. And in that case, we don't use the Hagedorn and Brown, the original one. We compute the liquid holdup from this equation, where the slip velocity, the difference between the gas and the liquid, is just set to 0.8 feet per second. And the way we assign the properties when this correlation or this correction applies is the same for the gravity and acceleration densities. They get the slip density. The friction now becomes, because the well is so liquid rich still, we're just going to use the liquid properties, both for the velocity and for the density. And the Reynolds number for computing the friction factor is just a function of liquid properties. Second one out is Bex and Brill from 1973. This is the most, call it, complicated one of them. It's the only correlation that really relies on flow regimes and calculating liquid holdups differently in each flow regime. It also accounts for inclination. So the way it works is that you calculate this liquid holdup at zero inclination at a horizontal pipe. And then you correct the liquid holdup at any angle between horizontal and vertical by this correction factor. So the horizontal liquid holdup is computed by an equation of this form, and this correction factor is computed by a more nasty equation, like the one shown here. And these parameters, A, alpha, beta, D, delta, epsilon, and Chi, I guess, they are dependent on which flow regime you're in. And the flow regimes, to estimate which flow regime you're in, there are equations to do that. I'm just going to show them here. So the original flow map that they provided in the publication was this one here. And you plot this liquid flux fraction against what is called a Froude number. And depending on which flow regime you're in, you select the numbers on the table on the previous slide. This flow map was later updated into this one, where they included a transition region. And in that transition region, you're sort of linearly weighing the solution in the segregated, if you're in a segregated flow regime and in an intermittent flow regime. That's what this transition accounts for. The friction factor also has a correlation, or sorry, a correction. I'm not showing the equation here, but it depends on the liquid holdup, the inclined liquid holdup. And finally, once the liquid holdup has been determined, you use that to compute the slip velocity, or sorry, the slip density. That's assigned to the acceleration and gravity densities. The mixture, or the no slip density, is assigned to the friction. And the Reynolds number is the friction factor, this one here. The uncorrected one is just computed with no slip mixture properties. And then it's corrected by this liquid holdup. This S here is a function of the liquid holdup. The third one is Gray, which is published in a user manual for, I think it's surface-controlled subsurface valves sizing program. It's essentially only applicable for gas wells, really. It assumes that there's mist flow in the well, the situation where there's dominantly gas and liquid either adheres to the pipe wall or flows as small droplets together with the gas. And it has a way of computing the liquid holdup. I'm not going to show the equation here, but what's also a little bit interesting with this equation is that it corrects the friction factor by calculating a effective roughness instead of the roughness that you provide for the sort of the pipe wall itself. It accounts for the fact that if there's liquid adhering, there's a film of liquid at the wall, the pipe wall may be more, call it, rough than what a dry pipe wall would be essentially, and that increases the friction loss in the pipe. Again, acceleration, gravity, they get the slip density, they most often do. Friction gets the no slip density, and the friction factor is computed with the Reynolds number defined as such. And the other input to the friction factor, or to the Moody diagram, which I'm not showing, is this relative roughness, which is the roughness divided by the hydraulic diameter. And that's where this gray correlation has a correction. So instead of using the fixed pipe roughness, it's using this computed effective roughness to increase the friction loss. Finally, we have a more recent correlation, the Wollesemayan-Gaillard. It's a publication that essentially just reviews a lot of correlations that are out there for multi-phase flow, and just tries to find one equation to fit everything. So you can see here, all of these are data points. They are for vertical wells, inclined wells, horizontal wells, different kinds of systems, different kinds of GORs, VOR, WR, ORs, etc. And they've sort of tried to find an equation that can more or less fit this data within some percentage. And I'm not showing the equation. It's quite nasty actually, but the gist of it is that you assign the slip density to all the three mechanisms, and you compute the Reynolds number with this definition to compute the friction factor. Okay, so that's how the correlations work in a nutshell. Further down, I'll give you some references to where you can find more about these correlations. But I think that's what we want to have in the course. Now we're going to go to the flow paths. By flow paths, we mean where does the fluid or the well stream go up the well? And there's different ways of doing this, depending on the completion in the well and depending on how you want to withdraw the fluids. Whitson Plus supports several. We can do casing flow, tubing flow, annulus, tubing and annulus, measured, and unknown. And they are selected. Each wellbore configuration has an associated flow path. Let's start with casing first. So there's always the option of either computing from the wellhead down to the top perforation, or providing some reference depth where there's a gauge and computing from the gauge and down to the top perforation. So if you have, for whatever reason, measured pressures at some depth other than the wellhead, you can set that gauge depth associated with the well configuration. You can turn on this calculate from gauge to sand phase using measured pressures. And if you provided measured pressures with the production data, the calculator will start at this depth instead of at the wellhead and compute down. And that may reduce the uncertainty quite a bit in these correlations. The closer you are to the true answer, the better. Same thing for tubing. Now we have a tubing installed, and the tubing flow path means we're just flowing up the tubing, either all the way to the well, either we're computing from the wellhead down to the top perforation, or from a gauge down. Annulus speaks for itself. That's when we're flowing up the annular space. Same thing there with or without the gauge. Then there's a bit special case. That's the tubing and annulus, or sometimes called parallel flow. That's when we flow both up the tubing and the annulus. So let's say we have the same pressure in both conduits, and then what the calculation routine does is that it solves for the split of flow of how much of this well stream goes up the tubing and how much of it goes up the annulus. And it does so by computing the pressure down in the tubing and down in the annulus. And it tests whether or not you get the same pressure at the end of the tubing for a given split of the well stream. If it doesn't, you have to update the well stream split is updated, and it tries again. So it's a solver routine. And then ultimately it'll find some split that accounts for some of the flow going up the tubing and some up the annulus. And then from the end of the tubing down to the top perforation, it's regular multiphase flow. Measured BHP has changed its definition or functionality since last time we taught this course, at least. What it does now is just echoing. If you're provided a measured BHP or some BHP in the production data, measured or calculated, but if you just want to echo that as part, for example, for a period of time in the production in the BHP of the whole history of the well, then you can use measured BHP, and it will echo it at the depth of the gauge that you specify. Then we have one that's new since last time, that's unknown. And unknown is essentially when you don't really know where the flow is going. Perhaps you've acquired an acreage or an asset recently that you haven't had time to investigate the different flow. You just want to get something quick and dirty. You can use unknown, and the logic there is quite simple. We're just assuming that the well stream flows against the smallest back pressure. So if there's a tubing in place and the casing pressure is greater than the tubing pressure, then then you're flowing up the tubing. So that's when the tubing has the lowest back pressure. If the opposite is true, if the casing pressure is smallest, then we flow up the annulus. And if there's no casing and no tubing installed, then it's really not a choice, it's casing flow. See, we have a question. Should you use tubing and annulus when you continuous flow through both? Thinking of scenarios when you intermittently flow up the annulus. It depends. I would say if you're in control as an operator of when you flow up one or the other, I would recommend to just have a series of well configurations where you assign the flow path each time you switch. If that happens very often on like almost a daily basis, then unknown is probably better, because you would see that the casing head pressure and tubing head pressure would flip up and down, and the unknown flow path would take care of that automatically. So two ways of doing it, if I understand your question correctly. Okay, artificial lift methods. So you have a couple of those. First one is gas lift, and gas lift we can do in 3 different ways. You can do what is called pour boy, which is essentially just injecting down to the end of the tubing and then up again. There's no valves in play. There are valves, no packer. It's just down to the end of the tubing and then up. You can specify one or several valves along the tubing with associated depths and closing pressures, and then the logic will find out which valve is open and put the gas in there. Or we have an automatic solution where we're trying to find at which point the gas is injected. That's where you typically don't know where the valves are located, but you just want to know approximately where the gas would be injected if the gas were free to enter the pipe anywhere. Just to go through those a little bit further, so if you have a tubing, if the flow path is tubing, then the injected gas goes down the annulus around the end of the tubing and then back up together with the well stream. If you have annular flow or annulus flow path, so-called reversed gas lift, then you're injecting down the tubing and back up the annulus together with the well stream. When we have valves in place, again, each valve will be given a depth and a closing pressure, and that closing pressure decreases with depth when it's measured at the surface. So what we will do is that we will use the casing pressure at any day, and we will compare it starting at the top. We will compare, okay, is this valve open? Yes or no? If not, then we go to the next one. If this is open, then we inject the gas there. If not, we go to the next one, and until we find the first valve that has a closing pressure less than the casing pressure. And then all the gas is injected there. For annulus, reversed gas lift, since these gas lift valves are strictly speaking one-way valves, then you can have the option that it's not always such that the last valve is a valve. It may just be an orifice or choke, maybe practically a hole through the pipe. In that case, annulus would go out the valve. If this last valve always open is ticked, that's what it means. If it's in sort of an orifice valve or an orifice, then that's what we're indicating. If that's not true, if all the valves have a closing pressure, then in annulus, then this would be all the way down to the end of the tubing and back up again, like poor boy. Automatic is when we compute. So in the well stream, the orange line, we compute the well stream plus lift gas from the wellhead down to the end of the tubing. In the annulus space on this side or the tubing on this side, we compute from the wellhead down to the end of the tubing just through pure dry gas. And then we try to find where these two lines intersect. And if they intersect somewhere along the tubing section of the well, then we inject the gas at the depth at which these two lines intersect. If for some reason, because of bad data or whatever, the correlations are inaccurate, if we cannot find any intersection, that this red line is always greater than the orange line, then we inject everything at the end of the tubing. So poor boy, that's always the limit. So the unknown flow path together with automatic gas lift can be a very powerful tool. You don't need to know very much to get very far with a well that has gas lift if you combine those two together. Rod pump splits the well into 3 segments when we're calculating it. First segment is from the top perforation to the end of the tubing. That's just regular multi-phase flow. Then from the end of the tubing then we go up the annular space where we assume that there's just a stagnant column of liquid with gas sort of percolating through it up to a user-defined liquid level. And from the liquid level to the wellhead, the third segment, it's dry gas flowing. And we recently made a change to the rod pump based on some feedback we got and some tests we made that showed that the solution we had in place were accounting for too much gas in this stagnant column of liquid. And what we discussed internally and some literature review was that we found that what most of us think when we think rod pump is that the pump is working, pumping the liquid up the tubing. And then there's going to be some liquid level, probably varies with time, in the annular space. But there's going to be a well-defined liquid level somewhere, and the gas is sort of going to percolate through that, either as so-called Dumitrescu bubbles or as just small separate bubbles. And we have now put in a model to account for this kind of flow. Then you have the more rare scenario, in which case there could be so much gas that in fact this gas going up the annulus is able to lift the liquids with it. And the sort of the critical point, if you will, call it the critical gas rate maybe, finding that and finding where you switch from this side of the picture to that side of the picture is something we're currently developing. Right now, we've just set that the critical liquid holdup is 0.7. So the liquid holdup can never be less than 0.7, and that will ensure sort of a liquid-like column in the annular space. But in the future, we will try to come up with some unified model that unifies every scenario going from no gas to essentially a lot of gas in the more rare scenario. And the idea here is that the liquid velocity in the annular space particular is 0, and the gas velocity is just the bubble velocity. So that's what we're estimating. We're estimating the bubble velocity, and then we're calculating the liquid holdup based on the difference between the gas and liquid velocities. ESP, we don't really model the ESP, the pump itself. What we're using the ESP for is just the measured pressures that you have at the inlet of the ESP, because then you can calculate from the inlet of the ESP down to the top perforation. You're going to be very close to the top perforation. So the ESP itself is going to give you a fairly good estimate of the BHP. What we're essentially doing is just correcting the change in reference depth. Really, that's what will happen. but we're not computing the pressure added to the ESP, not from the wellhead down to the ESP through the ESP. If we were to estimate the delta pressure the ESP adds, then there's going to be, and you would have to know very specific things about the pumps themselves and how they work, etc. Plunger lift is not an artificial lift method that we support, but we're just gonna I'm just gonna show this slide briefly just to say that there are ways to approximate it by using rod pump, the rod pump model, and adjusting the rates a little bit. I'm gonna leave it at that, but it is possible, but it's gonna be likely very approximate. Okay, last tuning. The one thing we also released last year was tuning of the BHP correlations. And the way that's done is that you have two factors that you can use to tune the correlations. These are multipliers. So the default value would be 1, 1. That gives you the default correlation. And if there's a different value from 1, that means that you've tuned the correlation. And the two things that we're tuning is the liquid holdup, the way we're essentially multiplying or shifting the liquid holdup, if you will. And the other one is correcting the friction factor calculation. So if you have measured data, both in the well through a gauge and preferably also at the surface rates that they are also measured, and you can do, you can tune the correlations to that data and use it perhaps on other similar wells where you don't have gauges, and hopefully that will give you an increased predictability or a better predictions of the bottom hole pressure. That's the main use case. A note of caution that I think is important to point out that we've seen a couple of times is that the majority of sources for BHPs, for measured pressures in the well, actually comes from ESPs. But unfortunately, we can't use those pressures for tuning. And the reason for that is that when we tune, we calculate from the wellhead down to the ESP. And the pressure we then would calculate would be at the outlet of the ESP. The gauge, however, is at the inlet of the ESP. So what the correlations will then try to do is to account for the delta pressure that's added on by the ESP itself. That really has nothing to do with the correlations. It's just a delta pressure that's added by the motor in the ESP. And you will have a hard time making the correlations predict that accurately. It'll probably drive the tuning into parameters that will render the correlations useless. So just be aware that the ESP cannot be used, as of right now at least, to tune the correlations. Okay, a couple of references. We have two sources of information that can be nice to review in addition to the slides here. The first one is a wiki. So we have a wiki.whitson.com. There's a page, or a couple of pages there on well pressure calculations and also the different correlations. There are more of the sort of equations and everything are described for each of the correlations. And then obviously we also have the manual for Whitson Plus. Also nice to get more the logic built in the BHP calculator and how it treats different scenarios. Last, it's just a teaser of what to come. One thing is the quiet side or silent side, or I've seen a couple of names for it. What we mean there is essentially that instead of going down, like in this case, you have tubing flow, instead of going down the tubing, relying on certain multi-phase flow correlations, we rather want to assume, well, there's a single phase static column of gas, most likely, in the annulus. We're going to compute the pressure down through that static column to the end of the tubing, and then only use the multi-phase flow correlations from there down to the top perforation. That would likely reduce quite a bit the uncertainty in the correlations themselves, because you're using them on a much shorter interval of the well. The fundamental assumption there again is that you can assume that there is a single phase liquid in this in the annular space in this case. For now, we're going to keep it a single phase. And the reason for that is because it's not often known where the liquid level would be if there's multiple phases in that annulus space. For gas lift, this can be actually quite useful and probably more accurate than computing down the well like we're doing now. And that's to go, instead of going down the well stream, we're going to go down, like in this case, when you have regular gas flow or gas lift, we're going to compute down to the injection valve through the gas column, and then the multi-phase flow correlations from there. And the main assumption you have to make there is that there's very limited pressure drop through the valve itself. So it's not, the valve isn't choking the stream and creating a large pressure drop. You have to assume that the pressures are essentially equal at the valve depth. So that will be quite useful for gas lift. Last but not least is something we've also been requested of, is to run our numerical models on tubing head pressure. And to do that, the numerical model needs a lookup table for it to take the tubing head pressure and convert it to a bottom hole pressure, which it then controls the model on. And the VLP table will be hopefully part of the next release. And what that essentially is that you provide a tubing head pressure, GUR, and a water hole ratio, and then one of the rates as well. And then the engine will be able, or the numerical model will be able to read out from that table what the BHP is for that situation. It's sort of interpolating between combinations of these. And the main use cases there is to, one, control numerical model on tubing pressures or surface pressures, or to compute surface pressures for an equivalent bottom hole pressure. So if the numerical model gives you bottom hole pressures, you want to know, okay, what tubing pressure does this account, or is this equivalent to? So it goes both ways. And that was it. 1 hour, 10 minutes, like I said, on the clock, it seems, at least on the recording. That's good. We'll take a short break, I guess, Matthias.
Yeah, we'll do a 15-minute break here. And then when we're back, we're going to do the exercises together. And I'll be running that show, so need some luck there. There's a couple of questions that I think we can just take as we are there, Stian, before we take the break. Has there been any discussion on attempting to model liquid holdup above and below the tubing anchor for rod pump? Or maybe you've addressed that already? Or
I can't remember that we've discussed that in particular, no. But we're very open for suggestions and feedback and comments regarding any of the models that we have, especially on rod pump. So, so if this is something that you have an interest in us looking at or expanding on, then just send us an email to support@Whitson, or to me personally, or to Matthias, and then we'll discuss it. But I don't think we've had a discussion on that particularly, no.
But if you have anything there, Jeff, just send it to us. I think you mentioned a paper one time. I don't know if that was related to this or something else, but feel free to shoot that. There's also a question from Andres here. We run discharge pressure gauges for ESPs. The challenge is how much of the pump is actually, how much the pump is actually seeing. Do you have any comment about this?
Not really. Sort of pump technical perspectives is not really my strong area. The only thing I can say is that if you have the gauge on the discharge side, then tuning would be easier from that sense that you're then computing actually down to where a gauge is measured, or where the pressure is measured, and not, you don't have to go through the ESP to get the measured pressure. Not entirely sure what's meant by the pump is actually seeing, but
can you elaborate on that?
So, but anyways, same answer there really as for the previous one. If this is a use case that would be interesting for, I guess this is marathon, then we're all ears. So just shoot us an email and we'll have a look at it. If it's just a matter of sort of having the choice of saying which side of the ESP you're measuring the pressure, then that shouldn't be too difficult to include, I think. If that has any value on like tuning and these things.
Perfect.
Okay.
Awesome.
Yep.
Yeah, so we'll take a break now, 15 minutes. Yeah, so yeah, and then we'll be back here at 1:50 Houston time.
Great, thanks.
So question, yeah, maybe you can answer the question in the chat there, Stian, as well.
Yeah, I will. I'm writing an answer now.
Okie dokie. So we'll go ahead and get started with kind of the second kind of part of the course today. And that's related to the exercises. And when we're going to go through these things, I would recommend everybody to have their slides readily available. The reason for that is that we're going to do a little bit of hand typing now when we're going to try to use this bottom pressure feature in Whitson Plus. The idea there is for everybody to be able to go through the different mechanics of the software, and it's also a way for you to also ask questions if there's anything you're wondering about. So in the slide deck, we're now in the part that's after the exercises and further down. And that's slide number 71. And the exercise is built and split into 3 different pieces. The first one is related to the general functionality of the bottom of pressure calculation. And here we're going to pay extra attention to flow paths and different artificial lifts. So we're going to first start with gas lift and then look at the 3 different options we have on gas lift. Then we're going to look at rod pump, ESP, something, and then we're going to look at something called BHP calculation setting. That's really powerful, especially when you're going to launch a bunch of different bottom of pressure correlations or calculations at the same time. Stian talked a little bit about the theory of tuning, so we're going to do that. And then the last thing we'll do, that's more a show and tell, but basically show you how all the things we're going to do manually, how you can do that very easily through a mass upload sheet if you're not using the API. Very good. So just again, just a quick reminder, we are using courses.whitson.com. A few of you have tried to go to courses.whitson.com and can't find anything, and that's because you're missing the HTTPS protocol at the beginning. So you can click this link right here. Maybe if I can also write the link again here in the chat. So I'll do like this. There we go. The other thing is that you'll use your username as an email, and you'll use the password Whitson with a capital W, BHP 2023. And if you have any issues, just ask in the chat here or send an email to support@whitson.com or to Stian, which is also here, and we'll help you to get access. So when you go into courses.whitson.com on any browser, this is what you're met with, and here you're going to put in your email, and here you're going to put in the password. Okay, so I'll do the same now, and I am a little bit unsure if this has the same. Then I'll continue with that. And once you've logged in, you should see that there is one field. It's the Permian field. And inside of that field, there should only be one project for you. I see there's almost 200 different participants registering for the course. So I see the project for every single participant here. Okay. So when I click here, I basically see all these projects. Well, you will see one of them. And the reason for that is that I'm a so-called super admin. So I'm a support user. So I can see everything so that I can help everyone if something is not working right. Okie doke. So once you've gone in here, you just need to find your project. I think I have a project here, which is called Matthias BHP course. And inside of this project, there's going to be 4 different wells. Okay, when you're inside here. So click fields, click your project, and go to wells. So basically, it'll be at the top here will probably be Permian, and the project will say most likely your email is what I think. Can people just give a reaction thumbs up if they've come so far that they see these 4 wells? And that's one of these guys. Perfect, excellent. Got an applaud there even. I like it. So great. So from there, we're going to go through the first exercise, which is related to gas lift. And gas lift is one of the things that we're really proud of in Whitson Plus because we can actually handle all the different gas lift mandrels if you have a little bit more advanced scheme. So if you have multiple different gas lift mandrels versus depth, instead of just assuming a pour bore configuration, which we also support, obviously. And the first kind of gas lift setting we'll use is the pour buoy. So then we assume that all the gas is entering at the bottom of the tubing. and that's what that thing is doing. So we'll start with first going into the well that has the gas lift name tag to it. So you see here there's 4 different wells, and we're going to start at the top and work our way down. So we'll click this gas lift well right here, and the second thing that we'll go ahead and do is to go to the production data tab, and there we can see all of this production data over time. A little trick, I know some of you, just seeing from the list here, some of you breed Whitson Plus and probably use it every day. Probably even much better than me on some of this, but the first thing we can go ahead and do is if we double click the gas lift right here at the top, that will be the only thing that is left on the screen. Okay, so everybody saw that. So if you double click the legend again, then everything else appears. And if you double click it fast, that's the only thing that will appear. So here we see that after a while, after around 37 days or so, we're starting to inject gas lift gas. Here also the very common question is, okay, are the actual gas rates in this period here and out, are they actually total rates? So basically the sum of gas lift and gas, or like, you know, actual reservoir gas. And here the actual red lines right here are assumed to be netted. Okay, so that means that we've deducted the gas lift gas. Okay, did everybody understand that? So it's basically the total. This guy right here is basically the total gas produced from the wellbore minus the gas lift gas volume. Okay. What we're going to go ahead and do is to go into the bottom hole pressure feature. That's the feature that we're going to spend all our time in today. So in the bottom hole pressure feature, if you click that, you'll see the screen right here. A very important thing for all of you is I would go, and this is a little bit important because some of you won't be able to follow unless you know this, and that's related to the zooming. So up here to the right, if you're on a large engineering screen, I would probably use a zoom of 80, okay, maybe, or 75, okay. If you're on a small laptop, you probably need to go down to 67, and that's just to be able to see everything on the screen here at the same time. Okay, and then we're going to open this well data card right here by clicking Edit Well Data. That's this button right here. Okay, and what we're going to go ahead and do now is we're going to enter this information right here, and we're going to enter it manually in this case, and then in some of the other cases, and when you do it for the API and stuff, it's of course possible to automate, but I'll just show you guys how to do this manually. And we're going to implement or include a very simple well or deviation survey with just 4 data points. Here we see that there are 4 entry points right here, while in the software we see that there's 3. So the way to make sure that we get an additional line is just to click the last row there and click enter. Okay, did everybody see that? So you just were in this line right here, click enter, and we are all set. And we'll start with inputting the deviation survey. Okay, that's the first thing that we'll go ahead and do, and then we'll input the perforated interval afterwards. Okay, and the first one at the top that's always set for us is always going to be 0. And then we have 150 and 150. And then we have 7,600 and 7,515, was it? And then 18,600 and 7,220. So that's the first thing. So I'll just repeat this again, zoom in a little bit so people can see it. So 150, 150, 7,600, 7,515, 18,600, and then 7,220. And you can also plot the deviation survey here now. There's a very simple deviation survey right here. Okay, this can be helpful in some cases. Like if you don't have the full well deviation survey, but you like have a simple PDF version of like a well diagram and stuff, it's very common to use this, and this, you know, it will still yield very, very good results. Then we're going to input the perforated interval. So that's 7,600 and 18,400, like this. Okay, so that's what we're looking at in this case. So right now, all of you should have this. Can people just let me know if that's kind of what they have? Yeah, looks like it. Perfect. Good. So that's the wellbore deviation. And now we're going to go to the wellbore data tab, which is the next thing at the top there. And again, just to, you can flip between these by clicking here at the top. And again, we're calculating the bottom hole pressure. That's basically the datum for that is this top perforation depth right here. So this one actually doesn't have any other impact than potentially plotting it in this plot. Now we have so few points, so it doesn't show here, but if you had more points, a perforated interval would have been shown here in this plot right here. Okay, okay. Question, Vianney, do you have a question there or? Maybe not. There's a. If you
no, I'm sorry. My apologies.
Yeah, no worries, no worries. That happened to me just now. Like I was gonna make a reaction and I clicked the raise hand. Anyway, happens to all of us. No worries. Awesome. So what we're gonna do now is in the next well tab, we're gonna put in some new information. And the first thing we're gonna go ahead and do is to add a casing pipe. Okay. So we're going to get 2 pipe numbers here at the top, and in general, these they can be fairly complicated in some cases. But what we're going to do here is to just click the plus icon right here up to the right, and we're going to actually input some of these things right here manually now. And then when we're going to do the tubing data, I'm going to show you that you can also use these databases right here of different configurations. And it's important for me to just emphasize that you can do both, because some people think that they can only do one or the other, but you can actually do both. So I'm going to start here with the line at the top here, and I'm going to make that 0 and then 7549, and the ID there is 4778, so I'm going to keep that the same. The roughness is always this number. You have to ask Stian why it's that number, but it's that number in every single software I know about at least. And then on the second line, we'll input 0, 18, 598 was it? Yeah. And then we're going to input, in this case, this number right here. Okay. I'm going to zoom in a little bit again so you guys see that on the screen if you need some time. So on the first line, there's going to be these numbers right here. And on the second line, there's going to be these numbers right here. And again, the reason why we spend a little bit of time, hopefully when you've done this once, you don't have to really do it more. You can use the API or you can use the mass upload sheet and stuff, but it's important for us to convey kind of the mechanics of this work and this workflow, if you like, because it's, we've seen some example where we try to jump straight to the automation, and just because we don't know some of the basics here, we've sometimes wasted some time on that. So just make sure that we're doing that. Okay, so that was the casing data. And now we're going to go to the tubing data. And what we're going to do here is that we will try to find in the database this the tubing with this ID and this OD. And by doing that, we click this database right here. Okay, and there we see there's a full list of data. And we're going to look for the one with 2375. And there I might have to have some, is that the OD 2375? Someone see that? 2375. The answer is
at the bottom there. There are several.
There we go. This one. So this one here, 2375. Everybody sees that. You can click this one. And there we go. So it populates here. You still have to provide the bottom MD though, which is 7325. 7325. That's the tubing. So now we basically said, now we're going to have a casing and a tubing installed. We're getting close now to add some more data. So hopefully everybody has gotten here. So we have casing data and tubing data. And for the other cases, we'll not spend time on this. I just want everybody to go through this at least once. Very good. The next thing we're going to go ahead and do is to dictate what the flow path is for this configuration. And we're going to use the tubing as our flow path. And since this is gas lift, we're going to go in and pick gas lift as our gas lift method. And we're going to leave it at poor boy for starters. Okay, so that's what we've specified right here. And again, poor boy, that just assumes that all the gas is entering at the bottom of the tube. Okay, or that it's basically the same as having a valve depth at the end of the tube. Okay, hopefully everybody has seen this, and now we're ready to click save. And once we've clicked save, we can just click calculate bottom of pressures right here, the top left, and the software will go ahead and calculate the bottom of pressures for us. Okay, and some difference here. We kind of designed this case such that the gauge pressures are actually not gauge pressures, just from some other tool, but we'll get back to that a little bit later. Hopefully everybody sees this right now, that we have 4 different correlations calculated at the same time. We have Beggs and Brill, we have Hagen and Brown, we have Gray, and Voldus Martin-Garrow. Okay, and we see they're very similar when there's predicted to be single phase in the tubing or casing, and they're more different leg time. Okie doke. Was that possible for people to do? So we just saved again, just to repeat. We inputted this deviation survey, we uploaded this ball data, and we clicked calculate bottom pressures. Excellent. So what we're going to do now is going to increase the difficulty level a little bit. We're going to do what we at least see that a lot of people that does a lot of gas lifts are very happy with, is the capability of handling multiple different valves along the tubing. So now we're going to change in the configuration, we're going to change to valves in the configuration here, right there. And then this thing pops up. And when we do that, we could input one valve. Let's say we input one valve, like a one valve system at 7,000. And we can click save. And this is just a one valve system, and I'll show you later how to do a multiple valve system. But just again, to show everyone, you go here, you change to valves, and then you click this edit valve button right here, and then you input 7,000 in this case. So we click save, and we just go ahead and calculate this one more time. Okay. Hopefully that was okay for people and that they got the result back. Now what we're going to do is we're going to have this option of inputting multiple valves versus depth. Okay. And that's something we try to kind of graphically explain here in the figure to the left. Stian also touched upon it briefly in the theory part as well. And the lift gas is injected through the first open valve all the time. And to know that, you need to know the valve depths, and you also need to know the so-called PSOs and PSCs. So if you've ever seen a gas lift tally example before, let me see if I have a gas lift tally. I think I maybe have one. Gas lift installation sheet. Let's take a look at that. Maybe you guys have seen that before. Hopefully you guys have. This is just a generic one. This is what the vendors provide. And it looks like this. So if you haven't seen it before, then great, that's your first time. If you have seen it before, it will be repetition. But it looks like this. And what you have here is basically these PSOs and PSCs. That stands for pressure surface open, pressure surface close. And then you have these intervals provided here in red. Okay, and then you have the associated depths right here. So that's basically what we're going to input for our case right here. We just have 3 different valves and the associated PSO and PSC. And again, we're going to do this manually just to get it in our fingertips. A little bit, quote unquote, not boring, but maybe not the funnest thing to do. But again, we go to well deviation survey, flip to well data, and open here. And here we're going to click add 2 times on the joints. We get this table right here. Okay. So again, everybody saw that. We go to valves, edit valve data, open here, and add 3 points. or 3 joints. So we're going to do 3,000, 5,000, and 7,000. That's the depth. And then the PSO and PSC is 1,100. It's 942. It's 854, was it? 854. 834. 782. 762. And then we click save. So just to zoom in for everyone, if they need to see what they're inputting. And again, this is why I thought it was good to have the slides there so you could actually see what the numbers are. Once you've inputted this, 3,000, 5,700, 7,000, and then these ranges, you click save again, and you click run. There we go. Awesome. The next thing that we're going to go ahead and do is to take a look at the option called automatic. And automatic is another option here in the gas lift configuration. It's called automatic. We're gonna input that. I'm gonna click save. Before we're gonna do that, I thought I could just go into the manual. So for those of you who don't know, if you're inside of a feature in Whitson Plus and you have a question, of course you can always reach out to support@whitson.com. We're really responsive. But if you just have a question about the theory and you would like to read upon it and try to understand it more, you can go to the user manual right here, and you can go and click. If you're inside of the BHP feature and you click the manual, you're brought into the BHP part of the manual, and you'll see that the navigation panel here to the left is exactly the same as the navigation panel here to the left in the software. Okay, the same order. And in general, the option that we're going to use now is what is called automatic. And here we can, for instance, find, okay, what does this automatic thing do? So automatic says that if the gas lift injection depth is unknown, then the BHP calculator can estimate that depth by computing the pressure profiles in the tubing and the annulus at the same time and finding the depth at which they're equal. If this depth is computed deeper than the end of tubing, then the end of tubing depth is what is used as a pour buoy. Okay. And when is this relevant? Well, it's really relevant in cases, especially when you try to hook up a bunch of different wells that you're running on gas lift, and you might have the gas lift injection volumes for every single well, but you don't have the gas lift valve depths. For instance, you've lost, you bought a company and they have 400 wells and you don't have a single well on the gas lift sheet, for instance. So this is a much better assumption than just using pour buoy, and that's what this is for. So now we've, again, hopefully everybody here in well data has used this automatic option. Click save, and now we can just calculate here one more time. And that's basically what we're trying to explain here with the graphics right here from Mo. Okie doke. Is it okay to follow so far? I see there was maybe a question in the chat. Yeah, so there's a question from Airbus here. Have you guys happened to compare the different methods to see what the difference between these cases, or if the difference between these cases is significant or not on the actual BHP number? And that's a great question. In some cases, even if you have multiple valves, you'll actually just inject at the end of the tubing or like at the lowest depth. So then, of course, there will be no difference. In other cases, it will be a much bigger difference. And some of these, some of these systems, they have valves from almost the top to the bottom with different ranges. So that's the question there is, in some cases, it's just really important and there will be a big difference in calculated numbers. In other cases, it will be basically no difference. So that just depends on the case, the surface pressures, and of course the injection gas rates, and of course the design of the gas lift system. Maybe Stian, you have a comment on that, or a sentence or two?
Yeah, I think that's really what you said. The dependency on the gas lift itself is, I mean, the deeper you can get the gas, the better it tends to be. And like you said, if you have the sort of the tally of valves, and for some reason the casing pressure, either it's set incorrectly or something that makes you inject all the gas at the first valve, then gas lift won't do much, right? Automatic is trying to be more pragmatic, but then again, it also relies on both the correlation in the well stream part being accurate, and also the wellhead pressures being accurate for that intersection to actually exist. If it doesn't exist, if for whatever reason the gas pressure is always higher than the well stream pressure, then you're also doing poor boy, right? So many of these cases defaults to something that's very close to poor boy, but I guess poor boy is, but at least poor boy is sort of a choice. Then it's always poor boy. With the other ones, you can essentially be more accurate.
Yeah. Awesome. We're going to go through, change gears a little bit. So we're going to go to a rod pump well. So back to your project right now, you can either go back to wells and click rod pump well, or let's say you're in the gas lift well, you can also go to the top here, and from this list, click rod pump well. Okay, so people see that. So either go to wells and click rod pump well, or just do that from the top here, and you're seeing this. In the production data now, in the production data editor, up here to the left. Again, if you want to edit this data, that's just up here to the right. And here we actually see that liquid levels are inputted here to the right when the rod pump is put on. So now we're going to take the difficulty level a little bit. We're going to actually have two configurations in this case. And we're going to have first free flow, and then we're going to have the rod pump system. So again, we're going to go to bottom wall pressure. And we're going to first open the well data right here. And now we see the well deviation survey and everything is inputted for us automatically. We see that the top perforation and bottom perforation is inputted, and we're going to spend our time in this well data card right here. Okay. That's what we're going to do now. So the first thing is that we're going to add a configuration. So this is initially just flowing through casing, and now we want to add when rod pump is turned on. So to add a configuration, this is the initial configuration from the first data point, and that will run to the second data point right here. And the time that we're going to use is 03/05/2015. Okay, so that you can do by typing 03/05/2015. That's one way of doing it. The other way of doing it would be if you let's say we didn't have anything here, you could go to the date by graphically clicking here. So the first thing would be to go to the year, that would be 2015, and then you would go to the month, which is the month 3, which is March. And then the day is 5 right here. So that's another way of doing it. So two ways to roam here. We can go either through the typing, or we can go by picking here at the top. So that's the first thing we need to know. And how do we actually know that it's that day? Well, we actually we can kind of see it from here, but you can also see it from the production data editor here when the liquid levels are coming on. That is the 5th of March 2015. So that's how we know that's the date. Okay, so still just being back here, when you added a configuration, you'll see here at the left that you can click back and forth between the different configs. The second configuration needs a some tubing data. So the first thing is that we're going to add tubing data. So when you add a new configuration, the last and previous configuration is what is being copied over. Once we have that dealt with right here, we're going to add a tubing data. So that's with the ID of 2441 and OD of 2875. So that was 244. Yeah, so that's this guy right here. So then ID is 2.441, and then the OD is 2.875, and the roughness is the default, and then the bottom MD is just 7022. We need to make the flow path tubing, and we need to change to rod pump right here. And once we've done that, we're basically good to go. Okay, so these are the changes that we're going to do. So I'll give everybody just like 15 seconds to make sure they've done this. Okay, perfect. And again, back to the rod pump calculation. When we calculate bottom pressures using the rod pump functionality, there's basically three things going on at the same time. And Stian, he mentioned this and touched upon this in the theory part. But just to break it down, from the end of tubing and down to the first perforation, that's just a regular multi-phase pipe flow, pressure drop calculation. That's just like free flowing through casing or tubing, or whatever, the size of this pipe is. The second segment is the end of the tubing to the liquid level in the annulus. And that's why we need liquid levels, because we need to know basically where this liquid level top is, okay? And that's a stagnant column of liquid, essentially. And the last thing is from the liquid level up in the annulus to the wellhead. That's where we assume single phase gas flow. Okay, so you're basically calculating these three segments together, and you're superposing them, and that's how you get the bottom hole pressure every single day during the pump. So what we're going to do now is that when we've clicked save, we're going to go ahead and calculate. Maybe there's a question, or maybe not. Just going to mute people. There we go. So here we have the results for the different correlations. And here we see that there's something going on. This looks kind of okay, and then we come here. But what is happening here? Can someone tell us that? Look at March 19 there. Someone have an idea what's going on? A little quiz. If you go back to production data, what is happening around that date? If you want to look at dates here, you can just click dates in the production data editor, and you see, looks like there's no production data in this period, right? And it's actually not. There was mentioned that there was maybe a shut-in, but it's actually not a shut-in. This is a shut-in right here, because all the phases are not producing. Here we see oil and water are producing, but the gas, for some reason, is zero. So what we're going to do now is to show a very cool feature in the software. So if everybody just goes to production data, here we definitely have seen just some bogus data right here. And what we're going to go ahead and do is to use the smooth functionality in the software. And we're going to apply that smooth functionality around this date right here. So that's 78, 76 to 79. So everybody go from the bottom of pressure feature to production data. Here we open the smooth functionality up to the right. And since we want to change something about the gas rate, we'll go here and say, I would like to change the gas rate. Okay. And in the gas rate, I'm going to pick this guy right here. And I want to use the smoothed version of the gas rate. And then I'm going to edit just a very small piece of this gas rate. So basically from here to here, I'm going to click this icon up here to the right. And I'm going to do like this. I'm going to click once here, and I'm going to click once over here. And what that will do is that will honor all the production data before, all the production data after, and in between here, it's going to come up with some fake data for us. Okay, and I think we had a question. No, maybe not. Okay, perfect. So hopefully everybody could see that. So now, when I picked gas rate up here, and I'm said I'm going to use that, see what's going to happen with your gas smoothed. Now, in this period of time around here, it's basically flat, what we should expect. And we see essentially no, abrupt GOR change or anything. So this makes a lot of sense. And this is very practical in cases where you see there's like, one of the faces, maybe like a fat finger or maybe a allocation issue or something like that. We can go ahead and smooth those rates. And it doesn't change the raw input of production data. It just changes the data that you use in your analysis. That's it. And if you now go back to bottom hole pressures and you recalculate, first of all, you see there's a little warning up here. And if you recalculate, you now see that this hump is gone. And there's a question related to the data point, if it needs data points on both sides. So for the gas rate, we need to bound the interval. So you can also zoom in here. So you need to have a point here and a point there. That's what we need to. So everybody saw that. I'll just go ahead and delete this now. And I'll say, okay, I'll not use it, just recalculate it again, just so people can see it one more time. So now we have the hump right here. We know what that hump comes from. It's that darn gas rate. We need to make sure that we smooth it out. So you can also go in here. You can go in and zoom in, for instance, and we see there's a gap here in the data. And you can just say, okay, I think it will be flat between here. It looked like that from the other rates. Click Save. Go to the bottom of pressure and click Calculate again, and that will be. Oh, I forgot a piece. Typical Matthias. Typical. I did not say use the smoother data. So I need to also say that I wanted to use it, which I did not do now. Typical me. So now it should hopefully do that. Okay. Does that work for everyone? There we go. I'll go and calculate it one more time, and this is what I get. Perfect. Excellent. Great. So now we've kind of answered this. Now we're going to go to ESP, and we could have done a little break here. But what I'm thinking is that we're probably just going to march through these, and then we'll just end the course a little early instead. I think that's better use of everybody's time. Okay, so now we're going to go and do the same thing. We're going to go to wells again, and now we're going to go through the fourth type of well, which is an ESP well. And again, this is something that you can navigate through here. Okay. And then the ESP well here. Or you can go into wells and just click there. And we're going to start with production data again. And here, when you have an ESP well, you need to have gauge pressures. And if there's a gauge failure, then you would use the smooth feature, and you would go in and say, okay, I would like to make some fake points between these points if you don't have gauge pressures. Because when you have an ESP, and the only thing you would like to do then is to convert from gauge pressure down to sand phase. That's what you would like to do. That's what we're going to talk about now. So with the production data, and at the top here, it should say ESP well. We're going to go to bottom of pressure. And in bottom of pressure, we're going to open the well data card. That's this card right here. We see that the deviation survey is already plotted for us. We see the top bottom perforation. And in the well data card, that's the second thing. That's where we're going to add a few things. Okay. So the first thing we see is that all the stuff here in the plot is basically provided for us, but we need to change the artificial lift method from none to ESP, because now we're going to use ESP. And you see what happens automatically then is that we get this calculated from gauge to sand phase using measured pressure. This toggle is now turned on. And this is also mentioned right here. Okay, and I'm zooming in a little bit so people can see that. But how can we actually convert from a gauge depth if we don't really know what the gauge depth is? So we need to also provide what the gauge depth is. So that's the last part right here. We're going to put in 8, 3, 3, 2. Okay, is that clear for everybody? We're going to convert from a gauge depth, then we need to know what that gauge depth is. And we're going to convert that to sand phase. So we're going to convert from here down to this guy right here. Okay, I'm going to click save. And once we're done with that, I'm going to click calculate. And what you see here, once you've calculated or converted all of those pressures from from the gauge depth to sand phase, you'll see that all the correlations are above the gauge pressure. And that makes sense, right? Because if it's going to flow from the fractures and from the perforations to the gauge, the pressure there needs to be higher, right? There needs to be a positive delta P in that direction. Okay. Was that a little bit fast or was it okay? So just to repeat, in well data, the only changes that we're making is just to make sure we set an artificial lift. Here we need, this is toggle on by default. We basically convert from sand phase, from the gauge to sand phase, and we need to provide a gauge depth as well. And this is very similar. Let's say you had a gauge in the well, but you did not have an ESP. You would do the same thing. The only thing is that, if it's free flowing or if you had it on gas lift or whatever, you would just not use ESP, but you would still, if you had none, you would still convert using this guy right here. Okay, if you had a gauge in the well. Excellent. Any questions about this? We're pretty straightforward. Was it okay to follow or too fast? People say that I talk too fast many times, and I've heard that since I went in kindergarten. So just ask me to slow down. If I've heard that enough times, I don't take that personally. But okay, excellent. The last part of exercise 1 is related to BHP calculation settings. Okay, and what that really means, it just is a setting that you can set here at the top, right here. And that was a great feedback. So just for people to see it again, well data, and there's a setting icon right here. That can be set by the API. If you are having, most of you guys have that automatically connected, or you can do it manually also right here on the front end. And why are these calculation settings important? Well, they're important because they set rules for how you're going to handle potentially improper data or incomplete data set. So, for instance, what are you going to do if you have a gas lift installed, but the gas lift rate is 0? Are you going to still just calculate it as its regular flow, or are you going to just not print out in calculation? The same for rod pump. If you have a rod pump installed, but you don't have liquid levels, should you actually calculate a bottom hole pressure, or should you just leave the liquid, or should you not print out anything? And the same with the ESP. If you have an ESP in the hole, but you have no gauge pressures, what should you actually do? So these are rules for you to set based on what you think makes sense. So if we go in here, for instance, and we go to the rod pump, and you don't have to do anything here. I'm just going to show you. And what I'm going to do is, let's say in this part right here where we have liquid levels, I'll just go in and remove some of the liquid levels. Yeah, so I'll just take a few of these days right here. Okay, save. And now I'm going to calculate. And if I calculate right now, you'll see that during this period of time right here without liquid levels, the software will essentially just assume this is a regular, casing or tubing flow problem in this case. But if I went in here now and I said, I would like to not compute rod pump when the liquid level is 0. Okay, and I click save, and I relaunch this calculation, what will happen is that the pressures here, if I take Hagen and Brown, is not being printed out. And this is especially helpful if you're connecting to Whitson Plus and you're taking those pressures and you're displaying them in some third-party tool where the production engineers are using it or whatever, Spotfire or whatever, some dashboards where you would like to digest it. And maybe you only would like to display trusted bottom hole pressures at that in that interface, for instance. Okay, so these calculation settings is just optionalities of what should be the default behavior if you have kind of bogus data, data that does not make sense. For gas lift, it might make sense that you actually have gas lift rates that's 0, even though you have it installed. Might happen, so that can be a case. But this is the preference is a little bit different from company to company, so this is just a flexibility for you all to have available. Excellent. Good. So what I'm going to do, I'm going to actually take back this exercise or that we're not doing a break, and we're going to do a quick break now, 10 minutes. So we'll be back at 2:45 Houston time, and we're going to finish with the last couple of parts. It will not be too much. So we'll be back here in 10 minutes. Okie dokie. So from there, we'll take the next exercise piece, which is BHP correlation, and then tuning that to measured gauge data. So we're going to do this on this well right here. So if we go back here, there's a BHP correlation tuning well. So that's the fourth well. And in that, we can look at the production data. We see we have gauge pressures. We need gauge pressures to be able to do this. And once we're happy with that, just looking at this, we can go to the bottom pressure. And that's what we see right here. And in the flow path right here, see we have deviation survey, and we also have well data provided right here. We're going to need to do two things. Now we have the configuration here. We have the casing data, we have the tubing data, we have the flow path, the gas lift, and the valves. But we also need the gauge depth. And that's in this case 7595. 7595. Okay. The reason why we need that is, of course, when you do the tuning, we're tuning to not the sand phase pressure necessarily, like that's very seldom, I think never, but we're tuning it to the gauge pressure. And the gauge pressure is at a certain depth that's different than the sand phase pressure. So all the calculations we're doing, they'll be done to sand phase, but the tuning exercise will be done to the gauge depth, and that's why we need it right here. So we'll go ahead and click save. And that's the only information we'll need here. And what we're going to do now is that we're going to go up to the right, all the way up to the right here. And again, I hope people are working on this well right here in their own project, and that they're in this feature right here, bottom of pressure. So up to the right here, there's a tuning feature. And we can go ahead and tune all of these correlations. But before we tune, I thought we could go ahead and just calculate the bottom pressures first. The reason for that, then we see what the delta is, even though this is not a true consistent comparison, because all the calculations, they're at sand phase conditions and or datums or whatever, or depths, while the black one is at gauge pressure. And here we see something is obviously off, because we know that the sand phase should be higher than the gauge pressure. Okay, so now we know at least a little bit of the difference. We see there's some difference here. We're going to go up to the right, and we're going to tune the Hagen-Brown correlation first. Okay, so we click tune here again, up here to the right, tuning, and it comes a little warning here, and you just click yes. So the idea behind this tuning exercise is exactly the same thing as we've done with PVT. So for those who don't know, we've run these large PVT consortiums in every single unconventional play in the world, big ones and small ones, and it's been really fun to be a part of. And what we've done there is that we've collected these PVT studies from all the wells where we have PVT. We've tuned one equation of state model to that, and then we can go ahead and use that tuned equation of state models for wells where we don't have that information. And it's the same idea in this example, where we have basically these bottom hole, or these wells with bottom hole pressure gauges. We tune the correlations to that, and then we can go ahead and apply those tuned coefficients to wells where we do not have gauges. Okay, so that's the whole idea there. And you can go ahead and actually do this for all the different correlations here. So we'll go ahead and do that. And right now we did it for Hagen-Brown. It's a little bit more of a computationally expensive exercise, but you know, typically don't have that many wells with gauge pressures. And once you're happy with these things, you just continue running them. And again, what we're tuning, that's what Stian covered in the theory part. That's the liquid hold-up correction factor and the friction factor correction. The last thing here is gray. Okay. So now remember my comment that we were tuning to pressures at gauge depth. Okay, so we can't make that or visualize that in the bottom of pressure, because in the bottom of pressure plot behind here, that's at sand phase conditions. So this show fit line right here is basically showing the comparison of the black line and these tuned correlations at gauge depth. Okay, so this is at gauge depth. And here you see there's not the same resolution. So what you know, in the tuning exercise, because the tuning exercise is kind of expensive, then we're picking 10 points, 10 or 20 points SSDM, like across the time series, and we're tuning to that. And it's like a moving average calculation and whatnot that goes in as a part of that. How many points is it again, Stian?
I think it's every 20th point. But there's also a sampling to avoid sampling offliers, and there's a little bit of logic behind this, how it works.
Awesome. Perfect. The other thing that we can see here is like, okay, there's something going on here. Like here it's pretty good, but early time we're still seeing the same difference that we're kind of seeing already. So what's happening here? Well, this region is where the wellbore is just filled with a single phase fluid. Okay, so there's not kind of multi-phase effects here. For this single phase region, tuning multi-phase correlations doesn't really make sense. So instead, to adjust this period, we need to adjust either the densities of the PVT or the water salinity. And typically, at least if you have a tune equation state and you feel good about the PVT part, maybe you would like to leave the PVT densities and maybe just go ahead and increase the water salinity. So that's what we would like to do now. So in the second iteration here, just click save right here. And now, just before we go ahead and do the salinity thing, you see now these tune coefficients have changed, so we need to relaunch the calculations, okay? Like here, and we see there's a difference here initially, and then it's pretty good late time, but still a something off here early time. So what we're going to do now is to increase the water salinity, and the reason why we do that, and we're going to focus on Hagen and Brown, and the way to do that is to open a well data card, and there's a water property right here, and we can go in and make this. Let's make this 50,000 for starters, and there's some reference cases right. Some reference values right here. So 35,000 to 250,000 is brine. Seawater is between 10,000 to 35,000. We start with 50,000 and we click save. And we go ahead and calculate that. What we'll see is that now, okay, we're getting closer in this region right here at the top. But 50,000 didn't seem like that was enough, so I'll go ahead and make this. This is like a manual thing, and it's primarily just for you guys to see, you know, how salinity impacts this calculation. Now we increase the salinity even more, and now we see we're getting, you know, closer to this endpoint right here. And I think I'll probably leave it at 100,000. Now we're looking pretty decent. Maybe I could go. Is there some upper limit here, Stian, that you would not, kind of on water salinity, that you would try to stay away from?
Yeah, so there are physical limits as to how much salt you can dissolve into water for a given temperature, and there's a correlation in the SP monograph Curtis wrote, phase behavior. I think it says about 260,000 ppm at 0 degrees centigrade. And then it increases with temperature as a secondary polynomial, essentially. So I wouldn't go above 300,000 ppm, I think, for any temperature.
Yeah. Everybody heard that? Let's not go above 300,000 ppm, but we could still go a little bit up maybe in this case.
Just one comment here. Since you defined the gauge at a different depth than the top perforation, it's important to point out that you don't want to use this plot to match the measured and calculated profiles. You want to use that show fit plot instead, because this will show when you recompute the tuning, that will show the pressures computed at the gauge depth, whereas the main plot in the feature will show you the bottom pressure computed at the top perforation, but the measured pressure is still at the gauge reference.
Yeah. So that's basically what, yeah, that's a good point, Stan, that, rigorously you would like to actually go in and do that comparison here and relaunch the tuning and show the fit here.
And if the tuning appears to give some funky results, I see now we almost have a factor 6 correction on the liquid hollow for Hagedorn and Brown. And the numbers you have in the table there, you can change manually, and the numbers that are currently there are sort of initial guesses for this regression that we're doing. So, for example, now that we've changed the water salinity quite a bit, maybe it's worth just going back to the default correlations. So just typing 1,1 and then trying to tune again and see if we get a better result.
Yeah. That makes sense.
Yeah, so maybe I have to save the coefficients first before you just setting them to 1 save and then open it up and tuning again. It's pretty
Yeah, but get different numbers now.
Okay. Yeah, that's true. So yeah, that looks good. So just keeping some of that in mind.
When doing it. One reminder is when it comes to the tuning exercise that you can't tune it to ESP pressures, and the reason for that is that basically what you're computing is at the ESP outlet, while what we're measuring is at the ESP inlet, and there's a delta P there, which I guess is the delta P across the pump, right, Stian?
Yeah, it would essentially be the extra pressure that the pump is providing to the well stream. There was a very good comment actually from I think it was from I can't remember who it was, but who said that when you measure it at the outlet of the ESP, you could in theory tune it, but then there is sometimes this ESP has a sort of like a built-in phase separation, so some of the gas is knocked out of the tubing and into the annular space, and so the well stream that you would be using from wellhead down to the ESP, even though you have the gauge on the right side, you won't have the right composition of that well stream because some of the gas has been knocked out into the annular space, and you don't know exactly what that split or that new well stream is made up of.
No.
That was actually a very good comment from.
Awesome. The last thing, and that's just something that I'll go ahead and show you guys. That's the last thing we'll go ahead and do in the course today. Then we've gone through basically the most important things. Let's see. What I'm going to go ahead and do is to show you guys the mass upload feature. So, all the stuff we did now is kind of populated for us, yada yada. But if you use the so-called mass upload feature, so if you make a project, Matthias test, whatever, I call that Matthias test, and then I use the mass upload feature up here to the right in that project, and I take that a file. So basically, that's a file that we're going to go and look at now together. But that's this file right here. That's just a template file. Here it has a couple of, it has a well, it has production data, it has well deviation survey, and wellbore data, 2 configurations over time. And here you can add as many wells as you like. And you can just go ahead and drag and drop that into the interface right here and click save. And that will update all this production data automatically for this particular well. And if you then go into bottom hole pressure, you see all the gauge data is there, you see the deviation surveys there, and you see the perforated interval and configuration data already, the 2 configurations. Just to make this very kind of explicit, the production data, that's what's in the production data sheet in that Excel file. So that's template right here. And then we have the deviation survey. That is the second step right here. So that's MD and TVD right there. Then we have the mass of the wellbore data. That's what's provided in this sheet right here. So it has all the wellbore data related to. That's basically all the stuff that's being uploaded here. While the deviation survey, that's what comes here. And then the production data, that's again in the right here. And there's also some basic information. You need some PBT information and whatnot on the first page as well. But that's it. And once you fill that in, you can upload as many wells as you want, and the software will eat it. And you can even then go in and mass, take all the wells in the project and bulk run PBT properties and bottom pressures and RTA and etc. once you've uploaded that. So that's a very efficient way, at least if you like to do a lot of kind of bulk runs in the software at the same time. Very good. So with that, Stian, I'm a little bit unsure if there's any questions at this point. This is actually everything we wanted to go through today. The objectives of these courses is to just make sure there's kind of short and to the point, and making sure we go through kind of the main functionality related to different topics. Again, we have already had one course this year like this, a virtual course, and that's the so-called PBT course that was in February. And now we're here on the bottom pressure course. There's an RTA course in June. In August, there's a flow material balance course, and in September, there's a nodal analysis course. And we are running those courses every single year. And they're virtual and with a similar group like this. Awesome. So, Stian, any last comments? Any questions about the material?
I don't see any questions in the chat, at least. I don't have any comments beyond that. No.
Awesome. Too easy. That's the people in the course. That's too easy for them. That's what it looks like. But awesome. I think with that, we'll just end the course now. And if there's any questions, we're always available on support@whitson.com. And just remember that if you send us an email, very helpful if you can bring this link at the top here in the email you sent, so we can see exactly what you are seeing on the screen. That will be able to help you very, very fast. An alternative to that would be to go and use this feedback form right here up to the right. Excellent. So with that, thanks a lot, everyone, and we'll hopefully talk here fairly soon, and you'll have a good rest of your Thursday, and eventually tomorrow it's Friday, so have a good weekend when that time comes around as well. Cheers.
Take care, guys.
Bye.
Thanks, guys. Thanks, Matthias.
Thanks, everyone.